Great. Okay, so we're now starting with the last part of this course, and actually I'm going to talk about advanced topics right now. Next class will be having a review of the second half of the semester and what we have done. And in the meantime, during the labs, you're actually going to work on your final project, which is the collision avoiding, it's a line following robot. And those slides will be available before the lab starts. So what about advanced topics? So let's first talk about the basic computer components. What we always see is a processor, we see a bus that's connected to a main memory, peripherals that all give their own input-output. So the whole idea is, so the question is, how do you actually connect the processor to the main memory and to all those peripherals? And what you really want to do is to have some kind of an addressing mechanism for this. So you can clearly have addresses to individual bytes that are stored in the main memory, but you can also allocate for yourself addresses to all your peripherals. And what you can then do is you can have some kind of, your own decoder over here that takes as input a bunch of, say, address bits that is then being decoded to either access main memory or, say, one of the peripherals that you're interested in. So that's what we are going to talk about. But let's first talk about the processor itself and about the type of computation that can happen. So take this example. In a non-pipelined fashion, suppose I want to wash my clothes, then dry them, then iron them, and then put them into the dresser. I can do one job at a time. But actually, my hardware is such that I have this all lined up in one pipe. So what I could do is, once I have finished washing my clothes, I can put those clothes in a dryer and at the same time start washing a new load. So that's what we mean by a pipelined computation. In other words, I do not add more hardware. I only use one washing machine, I only use one dryer, one ironer, and one dresser, but I can do useful work in all of those hardware components. So here we see that a first job called A starts, but once the washer is available, job B can start. And then job C can start once B has finished washing, and so on. So what you can see here is a pipelined fashion where all the hardware is continuously computing, and in this way you can actually reach a much higher throughput of computation. So in a processor you will do the same. So the whole idea is that the instruction execution can be partitioned in a fixed number of executions. The first one is fetch, like instruction comes from memory. The second one is decode, so you have some operation code together with the operands, and then you need to execute it. So you need to get the registers values that contain the values that you may want to add together, and then put them back into the register and so forth. So these stages over here can be executed in parallel, so each of them have a separate piece of independent hardware, and so you have a pipeline of how an instruction is being executed. So you first do the fetching and the decoding and so on. So that will be leading to increased throughput. And so what you need to be careful about is that if you're thinking generally about pipelining with code instructions and code sequences, well, there may be dependencies among the different instructions or how instructions are being executed between the different stages of those executions. And if that's the case, then you have to be very careful. So you may have to wait with one code execution because you need to wait till the other code execution truly has finished. So why would that be? Well, for example, I may only want to start job C once I actually have the trousers that were washed in job A, and I've wore them on at this particular moment, and now they get dirty. So I need to wait till job A has finished before I can do job C. In that case, I cannot pipeline it optimally. I have to push this out a little bit to this particular moment. In other words, if you're thinking about operations, maybe one register gets populated after an add instruction, and if that register is used in another instruction right after it, well, I still have to wait till the proper value of the previous add instruction really gets into that register before I can start using that in, say, a jump instruction or something like that. So these types of dependencies lead to stalling of the pipeline, because you need to wait till something is truly finished. And developing techniques to avoid those stalls is a hot topic in microprocessor research. Alright, but let's have a look at the basic concept here, which is that we use this three-stage pipeline where we do fetching, decoding, and execution. And it's pretty straightforward. You just say, okay, I have an instruction A that I'm going to fetch, then I'm going to decode it, but once I'm decoding it, I can already fetch instruction B. And then here I can already fetch instruction C. And this, now when this is all finished, I can fetch D, because this particular fetching hardware is available because it's not being used by any of the other pipelines. So this is what you would do. So now you can see that amortized, even though I need, say, 3 blocks of execution, it does not cost me truly that amount of time to do my executions. It's amortized in a way, because I'm fetching an instruction every single clock cycle. So the throughput is much more. I do have some latency. I need to wait another 2 clock cycles before this fetch or this instruction A is finished. So the latency is still there, but the throughput is much higher. So that's pretty cool. So that's what you will do in processor architecture design. Okay, so let's talk about the bus and the main memory. And then later on we'll talk about how we can bring in peripherals at the same time. So let's have a look. So if we look at main memory, we see volatile memory and non-volatile memory, different options. And you may have actually different kinds of memories available to you that you want to address. So when you look at memory architectures, there are essentially 2 kinds. The von Neumann architecture is one in which the memory is viewed as a long, one big memory that contains both instructions and data. And you really don't, when you just look at a memory, there's no difference between any of that. No difference when you just look at what is being stored there. It seems all the similar type of data, but it is a mixture of instructions and data. The Harvard architecture is using, is really recognizing a difference between the data and the instructions, and it physically separates the memories and also the buses for data, respectively instructions. So you have 2 separate components. And that may be useful. You may have different word lengths for data compared to that of instructions. And what current processors are doing is a hybrid architecture. The Harvard architecture, you have a picture in the next slide, is used between the CPU and the cache memory. I will explain in a moment. And in case that what you want to find is not in the cache, then you have a cache miss, then you need to go outside of the CPU, you need to go to DRAM, and that's where you will have a von Neumann architecture. So if you look at this, you have a von Neumann architecture where the CPU effectively has memory with data and instructions all together. The Harvard architecture is one in which the CPU is connecting, has a separate instruction memory and a separate data memory. And the hybrid is such that we have multiple memories. The cache is very close to the CPU, it's very fast, so you hope that what you want to use is actually in your cache, so that you can immediately fetch it and and compute very fast. There's maybe only 10 cycles. You have different caches actually. You have what we call an L1 and L2 and also an L3 cache, certainly in a multi-core processor. Let's say your L2 cache costs 10 cycles. If it's in your L1 cache, even closer, you have say 1 cycle latency. But if it's not in your cache, you need to go out of the CPU and it costs you about 100 cycles to get it from main memory, like DRAM. So what you see here is that both the data and instructions are all in that main memory, and they're being fetched but then put separately in their own either data cache or instruction cache. So now the CPU can first ask when it wants to fetch an instruction, it can look at the instruction cache. If it's there, you're happy. If it's not, oh, okay, then I need to fetch something from the main memory where the instruction is. It takes me some time. I'll put it in my cache. I need to evict something else out of it back to the memory in order to create space. And of course I want to have a mechanism in a way that I'm not doing this in a stupid way. So then you can start thinking about all kinds of tricks in order to make this computation fast. Like I can have some pre-fetching logic that sort of remembers what I am likely interested in if I look at the future instructions that I will be executing in the future, so I can already start fetching stuff in advance. It's also a kind of pipelining, if you will, in order to make the throughput higher. And when the throughput gets higher, your final execution time gets much smaller. So that's what the processor does. So let's now talk about parallel bus systems. We did talk in block 5 about SPI, microwire, I2C. Before that we talked about UART. Next, in the advanced course we talk about the CAN communication network and Bluetooth. We also talk about Wi-Fi, but it's just very basic, and ZigBee as well. But now we're talking about the parallel bus system, because we want to connect the CPU not just to the memory, but also to other kinds of peripherals. So let's have a look. So we have other devices, and what we will be doing, we will have a few pins that we're going to use for this. One set of pins is used to communicate data, one set of pins is to communicate addresses, and one set of pins is sort of an enabler, right? So which of these devices do I actually want to communicate to? So what we see here is that I need to recognize, of course, which one I'm interested in. So this particular control line will, for example, tell some peripheral that, okay, you should actually look at the data, you should actually look at the address, and then the processing in that peripheral will happen. So we use this 3-bus system, which is a common way of doing this. So the address, the data, and the control are separate lines that we use for the communication. All right, let's have an example. So we're building towards that. So say we have a range of memory locations that is addressable by the processor, and typically reflected by the width of the address bus. So say we have 16 bits would be 64 kilobyte, 32 bits would be 4 gigabyte. So if I have a 32-bit address, then I can address 4 gigabyte, right? So the linear, I should say it differently, sorry. If I have 2 to the power 32, so if I have 32 bits, then I have 2 to the power 32 locations, and suppose that each location stores 1 byte, then it would lead to 4 gigabyte. Alright, so I have a linear flat address space, it's just one contiguous block of bytes, that's what you can do, where the logical addresses reflect the actual physical addresses. So they're actually the same. We can also have a slightly different situation where we use pages and segmentations. So now we organize the memory into pages or segments with offsets, And the idea is that these pages are going to be your logical addresses, and the conversion needs to be made between the logical and the physical address, and you need that. So you also need to know where to be in the page and so forth. So if you are thinking about it like that, then what you need is an actual address translation unit. Alright, so here's a simple picture. Say you have program memory, which ranges from is this large, for example, and in your MCU, by the way, you have this data memory, and I think you can also see this in the datasheet, by the way, where the first part is all reserved. You cannot touch that. You have the 32 registers that you use for your computation. You can, if you do context switch and so forth. No, that's actually wrong. You have 32 registers over here with the pointers that you need for the different interrupt service routines. Then you have the 64 I/O registers. You have other kinds of stuff, internal SRAM, and so this amount of memory you need you should not touch this. This is actually this is what the MCU actually is using. And then you have external SRAM, which is all the rest that you can use as a programmer. Alright, so suppose you want to address this memory. So again, here we have the internal memory, which was what we saw here, this particular part, the 32 registers up to the internal SRAM. And then we have all the other external memory. Now, what we're going to do is that we're going to interface with external memory. And how do we do this? Well, we need to supply the address and data. We're going to multiplex the pins. So we have 8 pins for data because we want to store bytes. But those 8 data pins can also be used to communicate address information. So we're going to use the low order address bus, and the data bus is going to be multiplexed, and the higher order address bus is just separate. So we're using total 16 pins to communicate to our memory. And then in addition, we have an address latch enable, which you will need to distinguish whether you're actually sending address information or data over these pins, and you need to of course explain to the memory whether you're reading or writing. So this is the picture for it. So here we see the 87 to 0, A for address and D for data, and depending on what it's being used for, right, you either push through a address and the data comes, and next you push the data in, and you will have the address coming over these bits, and then you indicate whether you want to do a read or a write. Okay, so in the data sheet you will see this particular picture where you see this particular diagram that talks about a timeline. So we have a system clock, right? And you want to indicate when you're going to enable this stuff. So in the beginning, you're actually going to just, you were busy with the previous address and the previous data. Now you're saying, okay, let's start again. Alright, then what do? I'll put in the address, my current address. Notice it's the most significant bits, the 8 most significant bits that I put on here. And I put the least significant bits of the address, the 8 least significant bits, over the DA lines. So that address is now being collected by the memory, right? It's right there. You will next indicate whether you're doing a write or a read. If you do a read, you can now collect the data that was at that spot in the memory. If you do a write, then you create this particular signal, and then you can overwrite the data with your new data. So it's pretty much the same diagram for write and read. It's just that you indicate separately what you are going to do. Now, what's the problem here? The problem is that the processor is really fast, and your peripherals may actually be slow. So you need to make sure that they are synchronized in some way. So what you may have to do is, so what's the problem? The data on the bus may be invalid when they are read by the processor because the processor is so fast. So what you are going to introduce is wait states. And for synchronous processors, that means simply you inject one or more extra clock cycles into the bus cycle in order to just wait so that the peripheral is then ready, has actually written the data, has actually given the data to you. But that peripheral may just be a little bit slower than your actual processor, and that's why you put in those wait states. For the asynchronous processor, then you need to just make sure the acknowledgement signal, you need to wait a little bit before you send that. Okay, so here we have the same diagram, but now we simply have this part is just copied. It's the same as on the previous slide, but now we have a couple of clock cycles, so we do nothing. So here are our wait states. For example, in this particular case, 2 wait states. So this is how you communicate to actual memory. Now what we want to do is, we want to actually communicate not just to memory, but also to a bunch of other peripherals. So here they are. In this particular example, we want to connect to one 32 kilobyte SRAM for data storage, and we also want to have digital outputs driving 24 LEDs. So 24 LEDs, we have 24 LEDs. We divide them up in 3 blocks of 8. So effectively, we're going to transmit a byte to 8 LEDs, and according to the pattern of 1s and 0s, we will turn those LEDs on or off. So we have 3 of those, so that means that we will have 3 8-bit latches to feed into those 3 times 8 LEDs. Now we need to make a memory map and address decoder for the system. So that's what we're going to do. We want to do it in a somewhat optimized way, so that our decoder is going to be simple enough. So let's think about this. We know that the internal space we are not allowed to touch. And we're going to use address space for the SRAM, and we're going to use address space for the latches that we're talking about. So what are we going to do? We have 16 bits over here, address bits, so we can address a lot. And the idea is that we effectively only need to use 15 bits in order to address our SRAM of 32 kilobytes. Okay, so actually more than that. Just checking here. It's not quite correct. I have to think about it. Anyway, our SRAM is going to be part of this configuration. You don't really, okay, yeah, so that's the reason. Okay, so yeah, let me explain my own confusion for a moment. If I talk about such a small SRAM, why do you need such a huge address space? You don't actually. But the point is that I can now, if I do it in this way, I partition all the address space into these blocks in a way that only involves a few of those address bits. So let me show you. So everything that maps to this block starts with 3 zeros. Everything in this block has a 0, 1 over here. Everything in this block has a 1, 0 over here, and everything in this block has a 1, 1 and a 1, 1 over here, and they all start with zeros up front. And only for the SRAM you have a 1 here. So it's very easy to only look at those 3 address bits, A15, A14, and A3, A13, to figure out who I like to communicate to, or what's the intention of my communication. So that's depicted in a different way over here. So whatever you put here, if it starts with 0, 0, 0, I'm really going into the internal address space. If I have 001, and whatever you put here, then I'll go to this particular address space, and so on. Now, how can I make the distinction? I use only those 3 bits, A15, A14, A13. Only if A15 is 0, that means that I'm communicating with one of those first 4 blocks over here. Then I'm interested in A14 and A13, that it's either 00 or 01 or 10 or 11, one of the 4, and I will output which one I'm interested in. Now in this way I have made a decoder that computes which latch I'm interested in. So now notice I'm only storing 1 byte in those 8 lets, right? That's just 1 byte, that's it. But I have just given this latch a whole range of addresses that all are associated to this latch 0. And that's the trick actually. By doing it like that, I build a very simple decoder. If I would not do that, and I would say, oh, only a very specific 16-bit pattern corresponds to my latch 0, then I have to create a decoder that takes 16 bits in, figure out which is which, and then I will be able to figure out which latch I'm communicating to. But now I only have to look at 3 bits, and that's it. So in other words, I'm assigning a much larger address space to this simple latch than I really need, but I do this in order to optimize my decoder in the sense that it requires the least number of components and area size. So if the A15 tells me that I'm not interested in this, so I have a 1 over here, then I'm going to connect to the SRAM. So here you see a block diagram now. So we have a bunch of address bits coming in, right? And we multiplex the data bits again with the lowest 8 address bits. Now, all these most significant address bits are all going to the latch 0, latch 1, latch 2, and the SRAM. It's all connected. I'm forwarding A15, A14, and A13 to my address decoder logic that we had over here. And as output, I will figure out whether, through this enabler, whether I'm interested in this latch, or this latch, or this latch, or this SRAM. If I'm interested in this SRAM, I also need all the other address bits. And that's everything, right? All the 16 bits, not just these, but also the ones that I have stored for a moment when I used this particular multiplex bus for the addressing the data. So once I have now addressed the exact location in this memory, or if I was interested in one of those latches, which latch, then I can send the data over the data bus, which is multiplex with the addresses, and it can then feed into the latch that I'm interested in and changing the on-off configuration of the 8 LEDs that correspond to this particular one, or the 8 LEDs over here, or the 8 LEDs over there, or